In this video, we are going to be learning about chemical reactions. When it comes to chemical reactions, understand that chemical reactions are, in other words, chemical changes. And as we learned previously, a chemical change occurs when a substance is converted into one or more substances with different formulas and different properties. Okay? Now, there are some indications that a chemical change or a chemical reaction is occurring, and they are outlined on the right side of our slide. As you can see, a change of color, the formation of a solid in a solution that was previously clear, meaning not clouded. Understand that the formation of the solid is also known as a precipitate. The formation of a gas, and because a gas is forming, we're going to see bubbling. The emission of light and the emission or absorption of heat. All of these represent things that we can observe, and it comes as a result of a chemical change specifically. When it comes to a chemical change, we need to write them as a chemical equation. And when it comes to a chemical equation, there are some symbols that you guys have to be familiar with. They are all outlined in table 7.4 in the textbook. Understand that the molecules that are reacting are always written on the left side of an arrow, and they're known as reactants. Note that you can have one or more reactants. And as we're going to see later, there are some reactions that start with one compound and end up with several. Okay? That's just part of the whole idea. Now, if you have more than one reactant, as you can see, a positive sign, it is utilized to separate them. On the other side of the arrow, so the arrow is always going to be pointing the product of the reaction. So these are going to be the compounds that are produced from a chemical change or a chemical reaction. Similar to the reactants, if you have more than one product, then understand that they're going to separate it by a plus sign. Now, the arrow just indicates the conversion from reactant to product. Understand that if a triangle it is utilized, that means that the reactants are heated. In addition to that, we can have the different physical states. For reactants and products. And as you can see, we have a little s for solid, a little L for liquid, a little G for gas, and AQ for aqueous. Aqueous is something that is new. Understand that aqueous means that we have an ionic compound or a compound in general in water. That's what aqueous means. And understand that these physical states will be written at the bottom right corner. Of the chemical formula for the compound that we are utilizing in our chemical equation. Now, one of the things that it is observed in chemistry is that chemical equations follow the law of conservation of mass. And the law of conservation of mass indicates that in an ordinary chemical reaction, no matter can be created or destroyed. What does this mean? That matter doesn't come out of nowhere and doesn't get destroyed and goes into nothing. Okay, so if in the reactants you have a particular element, it will show up in the product. So as you can see here in the bottom, you can see that we have, I'm just going to zoom in. We have silver reacting with sulfur. So those two elements must be present in the product. And as you can see, Hg2S is what is formed. Additionally, no change in total mass occurs in an ideal world. So as you can see, if you add the two amounts in the first two balances, that's going to equal the product. Okay. That said, it is in a perfect system when there's no spillage of the product and the reaction went to completion 100%. Now, along with that, understand that the mass of the product is going to equal the mass of the reactants, but more importantly, we're going to learn later that it is important that when you have a chemical reaction that we balance it and we illustrate that the number of atoms are going to be equal on the reactants and the products. Now, as I was just mentioning, when we have a chemical reaction, we actually need to write a balanced chemical equation, because that balanced chemical equation is respecting that law of conservation of mass that it is present in chemical reactions. So in a balanced chemical equation, as you can see, no atoms are lost or gained. That means that the same elements that we start with are the same elements that are going to be in the products. Now, the number of atoms on the reactant side has to be equal to the number of atoms that we have in the product side. So as you can see in the following reaction, we have carbon in solid form reacting with molecular oxygen or oxygen gas. They are being heated with one another, and that produces carbon dioxide gas. If we look at the number of atoms in the reactants and the products, notice that we have one carbon, two oxygens, and in the product, we have one carbon, two oxygens. So it is said that this equation is balanced. So how do we write a balanced chemical equation? These guidelines will help you to determine how to balance a particular chemical equation. Now, as you can see, the first thing is that you're going to write the skeletal equation by writing the correct chemical formulas for each of the reactants and the products. It is very important that you know how to write chemical formulas, because if not, you cannot do step one, which is crucial. Then, if you have an element that occurs in only one compound but is on both sides of the equation, that's the first thing you balance. Then, if you have an element that occurs as a free element on either side of the equation, that's the last thing you balance. Now, if the balance equation contains coefficients that are fractions, you need to change these to whole numbers, because one of the exercises when we balance is that we're going to put whole number coefficients in front of the chemical formulas in order to balance the reactions. One of the main things that I'm going to highlight, and please do not forget, is that when it comes to balancing, you can only place coefficients. That is a whole number in front of a chemical formula. And we're going to practice so you guys are able to see how that is done. And understand that you never, ever, 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 okay? Let me just underline it. Change the subscripts. Because if you're changing the subscripts, you're changing the identity of that chemical formula. So, as you can see on letter F in our in-class worksheet, we have some problems, okay, where we're going to write the chemical formulas of the substances that are present, and then we're going to balance them. So I'm going to do all four so you guys see how this is done. So in the first one, we have solid potassium oxide. So we're going to write the chemical formula, which is K2O, and it's in solid form. As you can see, that's reacting with liquid water. So we're going to write H2O and then the little L. And that is forming KOH, which is potassium hydroxide. And that potassium hydroxide is in solid form. Now, We always make the list between the reactants and products of the atoms that we have and the number that we have. So we have in the reactants potassium, oxygen, and hydrogen. Remember, if we respect the law of conservation of mass, we know that we also have potassium, oxygen, and hydrogen in our product. So that being said, now that we understand that those are there, then we're going to look at the subscripts, okay, for the atoms to see how many do we have. So if we look on the left side at the reactant, as you can see, potassium, we have 2. Oxygen, we have 2 of them. And hydrogen, we have 2 of them. When it comes to the product, we have 1 of each. So the way that we balance this equation is if we place a 2 in front of KOH, understand that that 2 is distributed and multiplied by the subscripts of the atoms that are in the product. So that means that our potassium goes to 2, our oxygen goes to 2, and our hydrogen goes to 2. And that's how we balance the first equation. Let's do the next one. We have aluminum in solid form. We have oxygen gas, which refers to molecular oxygen. Remember that oxygen is diatomic, so this is O2. That is going to form aluminum oxide, and aluminum oxide is going to be Al2O3. So if we make the list of the atoms that we have, and I'm just going to do it to the left side of the slide, we have reactants, we have products, and in this one we only have aluminum and oxygen on both sides. We start with 1 aluminum, 2 oxygens. In the products, we have 2 aluminums, 3 oxygens. So when it comes to this, one of the things that we can do is actually increase the overall number of our oxygens, because as you can see in the left side is going to be even, and then on the right side is going to be odd. So let's just find a value that is common between 2 and 3. So if we place the value of 3, I should start on this side. If we place the value of 2 on this side, then that means that I'm going to take my aluminums to 4, my oxygens to 6. So then if I put a 3, wait, I took the notes in the wrong side. We take our aluminums to 4, our oxygens to 6. That means that if we put a 3 before O2, then we're going to take this to 6. And then lastly, to balance our aluminums, we're going to place a 4 in front of it. For number 3, our chemical formulas are the following. We have aqueous sodium peroxide, which the chemical formula is Na2O2. And as you can see, we're going to put an AQ. This is reacting with water, which is a liquid. Then we're going to have sodium hydroxide, which is an AOH in aqueous form. And lastly, we're going to have oxygen gas, which is O2. Okay? So when we have this one for reactants and products, we have sodium, we have oxygen, we have hydrogen. On the other side, we have sodium, we have oxygen, and we have hydrogen. So in our reactant so far, we have 2 sodiums, we have 3 oxygens, and we have 2 hydrogens. In the product, we have specifically 1 sodium, we have 3 oxygens, and we have 1 hydrogen. So the thing is, like, at first it appears that our oxygens are balanced. So then we have to take into consideration what is happening at the level of our sodiums and at our hydrogens. Okay. So when we take that into consideration, then we have to think about, okay, so at first I can start by saying, well, I can balance specifically the number in terms of the sodiums, for example. Okay. So at first, you could start by suggesting, if I place a 2 in front of my sodiums, okay, then what you're going to do overall is that you're going to increase sodium to 2, but then that affects everything else. Your hydrogen goes to 2, but now your oxygen went to 4. So now we balance the sodium and the hydrogen, but then our oxygen is off. Okay. So when you do that, then you have to find a way in which you're going to balance, okay, your oxygens. So right now, what you can do is that if you try to balance your oxygens, okay, by placing a 2 in front of the water, then what you're going to do is that now you're going to increase your number of oxygens to 4. But guess what? Now your hydrogens went to 4. Okay. So remember that there's only one spot where you have hydrogen on the products. So possibly this value of 2 is not correct. Okay. So if I remove the 2 right there, okay, then I have to say, okay, if I remove that 2, let me just remove those numbers that I put there. Let me just go back to my original count. Let me try to do something in which I balance the hydrogen. So if I balance the hydrogen, then I can just place a 4 right here. And if I do that, then my sodium goes to 4. My hydrogen goes to 4. And then my oxygens go to 6. Now I can ask myself, well, my hydrogens are balanced. My oxygens and my sodiums are not balanced, but they're honestly just off by a factor of 2. So if I place a 2 in front of my sodium peroxide, then my sodium, because we're multiplying 2 times the subscript 2, they're going to go to 4. Okay. My oxygens, we're going to say 2 multiplied by 2, that's going to be 4. And then 2 multiplied by 1, that's going to be 6. Now my equation is balanced. Let's move on to number 4. So the chemical formula for potassium chloride is KClO3. As you can see, that's a solid. And then we have KClO4, and that's also a solid. And then we have KCl. That's also a solid. Now, if we make our list for reactants and products, we have potassium, we have chlorine, we have oxygen, and those are the elements that we have on the other side. So taking that into consideration, I'm going to make my list. Potassium, I have 1 of them. Chlorine, I have 1 of them. Oxygen, I have 3 of them. Now, on the product side, I have 2 potassiums, I have 2 chlorines, and I have 4 oxygens. Now, when it comes to this, one of the first things that we can do is try to balance specifically, let's see, the potassiums. So what if we start putting a 2 here in the beginning, okay? Then that means that my potassiums will go to 2, my chlorines will go to 2, and my oxygens will go to 6. Now I have balanced my potassium and my chlorine, but my oxygen is off. Now notice that my oxygens on the product side have a 4, okay? So if I have a 4, then one of the things that I have to take into consideration is that, well, since I need 6, maybe that number 2 is not going to be the correct way to balance this, okay? Because I only have those oxygens in one side of the molecule. Let's just try a different variant, okay? What if, for example, we start making changes on that KClO4, which is the potassium perchlorate. So what if we place a 3 in front of it? If we do that, then we're going to change that potassium to 4, because here we have 3 times the 1, and we also have another one right here, so that's where the 4 comes from. Then our chlorines will go from 2 to 4, because remember, 3 times 1 plus this one, that's 4. And then our oxygens are going to go to 12. Well, if we see here, by putting a value of 4 in the beginning, then 4 times 1 takes our potassiums to 4. 4 times 1, it takes our chlorines to 4. And 4 times 3, it takes our oxygens to 12. Now, our equation is balanced. Every time we don't have to put a coefficient in front of a compound, as you can see, we can actually place the value of 1, because typically the value of 1 is actually omitted when it comes to the coefficients. It is very important to practice as much as you can balancing equations, because balancing equations, there is no set rule. Is based on trial and error. So it is very important that you do your best, that you practice as much as you can, go over the worksheets, go over problems as much as you can. Now, even though in the worksheet we don't have a problem specifically for double replacement reactions, one of the things that I want to go over is how to balance double replacement reactions, because one of the things is that sometimes those can be a little bit overwhelming because students don't understand how are we really going to be balancing the equations when you have all the atoms that are present. So understand that I'm going to do the following problem. So this is balancing double replacement reactions. So I'm going to give you the following example. We have PbNO3 2 in aqueous form plus NaCl in aqueous form. That forms PbCl2 in aqueous form plus NaNO3 that PbCl is in solid form, and then NaNO3 in aqueous form. Okay, so when we have the following reaction, one of the things that we can think is, okay, In this double replacement reaction, I can see that my polyatomic ion, NO3, shows up in the product as NO3. So when you have that situation, this is how you tackle it. You're going to say, in my reactants and in my product, this is what I have, and these are the atoms that I'm going to count. I have my lead, I have NO3, I have sodium, and I have chlorine. And the reason why we can treat NO3 as a unit is because it shows up in the products as a unit. So here we have Pb, we have NO3, we have sodium, and we have chlorine. Okay? So if we look at the reactant, we have 1 lead, we have 2 nitrates, and it comes from this value. That's where this 2 comes from. We have 1 sodium and we have 1 chlorine. As we move to the product, remember this is the reactant and this is the product. We have 1 lead, we have 1 nitrate, we have 1 sodium, and we have 2 chlorines. Okay? In a situation like this, for me, the easiest thing to do is just to start balancing that polyatomic unit. So in order to do that, I have to put a coefficient of 2 in front of that sodium nitrate to take my nitrates to 2. But remember, putting a coefficient of 2 in front of that whole compound is going to take my sodiums to 2. Now, as you can see here, the only thing that I have left to balance is going to be my sodium and my chlorine, which is in the reactant. And by placing a coefficient of 2 in front of sodium chloride, it will take my sodium to 2, my chlorine to 2, and now my equation is balanced. So I will encourage you that if you have a double replacement reaction and you have a polyatomic, that it is in the reactant and it moves and it shows up in the product as a polyatomic, please treat it as a unit and go ahead and practice and master balancing equations.